So I'll talk today about Bandana, a system that uses non-volatile memory for storing deep learning models. And this is joint work with colleagues from Facebook and Stanford. In this talk, I'll focus on recommender systems. So before we dive into the details, let me give you some background on how these systems work and why they need so much storage. So let's take, for example, the case of matching a user with the most relevant posts. Imagine that the user logs in, and then we compare the user with multiple posts. And we try to predict the probability of a click for each post. The idea is eventually to show the user the posts that are most relevant for the user. And the question is, how do we generate this prediction? So we do it based on the past activity of the user, for example, the pages liked by the user, and we do it based on the main characteristics of each post. For instance, the main words in the post. In general, we call these features. We then feed these features into the neural network, and the neural network will generate us the probability of a click. Now the question is, how do we represent this feature? What exactly do we provide the neural network? So let's take, for example, the feature that represents the pages liked by the user. And let's imagine that these pages are movies. And the straightforward way would be to just assign a unique ID per movie. And if a user, for example, like the movies Shrek and The Incredibles, the feature vector would just look like this, 1, 0, 0, 1, 0, and so on. The problem with this kind of representation is that we don't know much about the relationship between the movies. So if we have lots of information about Shrek, but not so much information about The Incredibles, we don't know whether we can apply information from one movie to the other. So what if we add another dimension? And the two dimensions that we use that can represent different things, for example, whether it's a children movie and whether it's blockbuster. And now we see that Shrek and The Incredibles, they share some things in common because both of them are children movies and blockbusters. And what if we add even more dimensions and keep an entire vector per movie? And the elements in these vectors, they can have different meanings. And these vectors is what we call the embedding vectors. And the table containing them is what we call the embedding table. So you can tell that these embedding tables may become very, very large, because here we see that we have a separate vector for each possible page. And of course, we keep a separate table for each feature. So one table will represent all pages, and the separate embedding table would represent all possible words. So in general, the embedding table may consume very high capacity. So let's go back to our example of matching the user with the most relevant posts. So we look at the past activity of the user and the main characteristics of each post, and then we load the corresponding embedding vectors for each feature. We then feed these embedding vectors into the neural network and get the probability of a click. So you can see that the embedding vectors are right in the critical path, because the neural network can't generate any probability of a click before we provide it with all the embedding vectors. And that's why the embedding vectors are usually stored in DRAM, because they are very performance sensitive in terms of latency and in terms of throughput. Let's talk more specifically about the embedding vectors in our workload from Facebook. So the embedding vectors in Facebook are actually much larger, and they can contain 64 elements or 128 bytes. They are stored in DRAM for performance. And in Facebook, there are thousands of servers that are only dedicated for storing and loading these embedding vectors in DRAM. And these servers are DRAM capacity bounded. As we saw, recommender system can require a very large amount of DRAM for storing their embedding tables, and the model sizes are only expected to increase in the future. Because DRAM is becoming prohibitively expensive, our goal was to design a cost-effective storage by storing the embedding tables in the NVM instead of DRAM. And why NVM? So first, NVM is cheaper than DRAM. but it also has better performance than Flash, with up to 10 times better read latency, and its endurance is also about 6 times better than the typical TLC Flash. And when I say NVM, it may be confusing because NVM has 2 different form factors. So one is byte addressable, that is based on DIMMs, and the other one is block addressable, that is based on PCI Express. The byte addressable NVM is faster, but it is also more expensive, and that's why we chose to use the block addressable NVM, which is not as fast, but still faster than Flash and not as expensive as the byte addressable NVM. Just to give you an idea about what I mean by replacing DRAM with NVM, so the idea is instead of storing all the embedding tables in DRAM, to only keep a very small layer of DRAM as a cache, and then store the embedding table in the NVM. The first naive policy we considered, which we call the baseline policy, is to simply cache the vectors one by one. So the lines that we see here represent the embedding vectors, and the squares inside the NVM represent the NVM blocks. So if a user liked a content that is associated with these 3 green embedding vectors, we first make room for them in the cache by evicting other vectors, and then we simply read these 3 vectors and allocate them to the cache. The problem with this policy is that even though we only read 1 vector out of each NVM block, we still have to read the entire NVM block because the NVM device is block addressable. So if the block is 4 kilobytes, we only use 128 bytes out of it. The read utilization is very low. We use the term effective bandwidth to describe the percentage of the bandwidth that is read by the application. And we see here the average NP99 latencies as a function of the application request throughput. And this is for the ideal case where the effective bandwidth is 100%. Unfortunately, as we just saw, in the baseline policy, this is not the case. And the effective bandwidth is much lower because we only use 128 bytes out of the 4 kilobyte blocks. And the latencies for the baseline policy, they look like that. So they explode very fast because we saturate the read bandwidth. So our general problem is how can we effectively store fine-grained data on a block device? Or in other words, how can we maximize the effective bandwidth? Another approach is instead of fetching the vectors one by one, to prefetch the entire block that belongs to the vectors that we are interested to read. And in theory, we get it for free because we have to read the entire block anyway. But unfortunately, this performed very badly and actually reduces the effective bandwidth by 90%. And the reason is that most of these prefetched vectors are never read, and the only thing they do is to trigger the eviction of more useful vectors. And that leads us to our first goal, which is storage partitioning, or in other words, how can we store vectors that are likely to be accessed together in the same physical location, in the same NVM block. The first partitioning strategy we explored is based on the values of the vectors. The intuition is that similar vectors might also be accessed together. For example, if a user liked the Incredibles 1, there is a very high chance that the same user also liked the movie Incredibles 2. So these 2 movies will be accessed together, and they share very similar embedding vectors. And for this kind of semantic partitioning, we can simply use a clustering algorithm like k-means. So imagine that these are the vectors, and we run k-means to cluster them into k clusters. And then we use these clusters to partition them into NVM blocks. These are the results after we partition the vectors using k-means. So the y-axis here is the effective bandwidth increase. The x-axis is the number of k-mean clusters. And the different lines represent different embedding tables or different features. So you can see that some tables get up to 3 times better effective bandwidth. And in general, the effective bandwidth increases with the number of clusters. But unfortunately, the runtime also increases exponentially with the number of clusters, and that's a problem. In the paper, we show that we ran k-means also in a more efficient version where we run it recursively in 2 stages, and it was much more efficient, but still, eventually we reached the conclusion that while k-means can provide significant bandwidth benefits for some embedding tables, in general, similar values do not guarantee similar access pattern, and for other tables, we didn't see any benefits at all. In addition, embedding vectors are frequently changed. In Facebook, it can happen every hour, and that means we will have to rerun k-means very often. So another approach is, instead of using semantic partitioning, to use the past accesses to predict which vectors will be accessed together. And for this approach, we use an algorithm called the social hash partitioner. Let's see how it works. We keep a list of the past queries, which are the squares here, and the circles represent the embedding vectors that are associated with these queries. And the objective is to minimize the number of blocks that satisfy each query, what we call fan-out. The first step is to initialize 2 buckets randomly, and then we try to find a pair of vectors which we can swap to reduce the fan-out. Let's see an example. So you can see that these 2 queries access both buckets, but if we look at vectors 4 and 7, we can swap them like that, and now each query accesses only 1 bucket. So we were able to reduce the fan-out. So we do this iteratively for all possible pair of vectors until we don't find any vectors to swap. And then we just split the buckets again and run the algorithm recursively until the bucket size reaches the size of the NVM block. These are the results after running social hash partitioner when we have unlimited cache, so no evictions yet. You can see on the left side that the effective bandwidth increases by up to 6 times for some embedding tables. On the right side, you can see that the runtime is less than 7 minutes for all the embedding tables, which is very reasonable because we intend to run it offline after training. But unfortunately, DRAM is not unlimited, and it is actually very limited. So that brings us again to the question, if we read 1 vector out of an entire NVM block, what should we do with all the other vectors? We saw earlier that without partitioning the vectors, if we just prefetch all the vectors, we decrease the effective bandwidth by 90%. So now, if we use the social hash partitioner and then prefetch all the vectors, it doesn't look as bad, but it still improves by only 1%, which is basically nothing. So that brings us to the second question, or the second goal, which is to design an effective cache policy that can maximize the vector hit rate in the DRAM cache. We tried several techniques in the paper, and the one technique that had the biggest impact is setting a threshold on prefetch vectors, or in other words, to only cache prefetch vectors that were read 3 times in the past. Here, for example, we see the effective bandwidth increase as a function of the access threshold for 2 different cache sizes, the yellow and the blue. The important takeaway here is that for different cache sizes and also for different embedding tables, we have different optimal threshold. You can see that for the yellow cache, the optimal threshold is 5, and for the blue cache, the optimal threshold is 10. The question is, how can we choose the optimal threshold? Ideally, we would want to experiment multiple thresholds, multiple configurations, but of course, this is very expensive. So instead, what we do is to run cache simulations. So we only sample a very small portion of the requests, like 0.1% of the traffic. And then we use these samples, these cache simulations, to create a very low overhead estimate of the hit rate curve as a function of the threshold. And apparently, this is a very good approximation of the right threshold we should use. So let's look at some end-to-end results. Here we see the effective bandwidth increase for different embedding tables, different features. And the different columns here represent different sampling rate. So you can see that these are the sampling rates that we use for choosing the Prefetch threshold. And you can see that even when sampling only 0.1% of the request, we still get a very similar effective bandwidth increase to when we use the full cache, which is like an oracle in our case. Here we see the effective bandwidth increase as a function of the total cache size. Again, the different lines here represent different embedding tables or different features. And it is not surprising that larger cache provides better effective bandwidth because it has more room for prefetches, and the evictions are less expensive in this case. So to summarize, to our knowledge, Bandana is the first system to leverage non-volatile memory for storing deep learning models. Our main takeaways are partitioning the embedding vectors based on the past access pattern, prefetching the embedding vectors based on the number of past accesses, and using mini simulations to determine how aggressively to cache the prefetched vectors. Thank you, and I'm happy to take questions.
Okay, go ahead.
Hi, I'm Rosamund Daya from Spotify. You mentioned that the vectors can change like hourly, and I would guess that if you want to do like a rollback or something like that to use previous vectors, that's something that happens sometimes at least. How does that affect like your partitioning strategy and how that interacts with any kind of secondary storage where you keep historic vectors for rollbacks?
So it's correct that it may be changed every 1 hour, and for k-means it is more meaningful because k-mean is actually based on the value of the vectors. For the social hash partitioner, we don't take these online trainings into account, so we only run it once in a while when we do, let's call it a larger training. So we don't run it every hour.
Hi, this is Alex from Google. I'm curious, when you were clustering the embeddings, why did you cluster them based on content instead of access pattern? Like the set of queries that have each embedding active or something like that?
So I'm not sure if I got your question correctly. So the first approach that we used was using the values of the embedding vectors. But then the second approach, which is the one that we use, like we don't read
when you were clustering the embeddings, which was the first approach,
yeah, in the first approach,
why did you cluster them based on the values instead of clustering them based on their co-occurrence patterns with queries? Because if you go, that would be actually robust.
So how do you suggest to do it?
You LSH?
With
there are lots of ways of...
No, so I think what you describe is similar to what we do in the second approach, right? Which is based on the access pattern.
Hi, Leon from McKinsey. You mentioned that you moved away from k-means because of the scalability issue, right? Did you consider choosing something non-parametric, like a Dirichlet process instead, where you don't have to define a priori?
So scalability was actually not the reason we decided to move out from k-means, because so I didn't show it here, but in the paper we showed that we ran k-means in a more efficient version, where we kind of solved the scalability problem. We ran it recursively in 2 stages, and that solved the runtime problem. We chose the other approach because we realized that k-means doesn't work for all the embedding tables, for all the features. For some of them, the values don't mean that the vectors will be accessed together.
But how do you define like k? How do you make this optimal choice? Is it defined in your
for the k?
Yeah.
So it's a good question. We didn't come with an optimal k, but we also, again, we show in the paper that I think we cannot. I also showed one of the graphs here that you don't need a very large K in order to get to the saturation point when you don't get better performance with a larger K.
Okay.
Go ahead.
Hey, Ash from Unity. I had a quick question on, in your social hash partitioner, how do you handle the problem of an embedding vector just never appearing, never having an access pattern, so a cold start?
Yeah, so it's a good question. Hopefully it shouldn't happen, but it may happen. So that's one of the things that we are trying to solve in the second part, where we use the number of past accesses to decide whether we should prefetch this vector at all or not. So in the social hash partitioner, if it was never accessed, it would just randomly be positioned somewhere. And then we hopefully will not prefetch it, because we will see that we don't have any past accesses, and then it will just never be prefetched.
So have you run experiments to see if this affects performance in practice? Because it's getting accessed, and that removes the advantage of loading a block at one time?
So I'm not sure what you mean. You mean that if... So we know that we can't partition the vectors with 100% utilization. That's exactly what we're trying to solve, again, by setting a threshold for the prefetch for the vectors that we prefetch. It's not, we can't reach the 100% utilization, but we're trying to maximize it as much as we can.
Agreed. I guess what I'm trying to understand is, at what point does it break down? Say there is a scenario where there is an X percentage of cold start vectors. Assuming that you're less than X, it works fine, and that you can load blocks and it's super efficient. You don't have that many cache misses. But then I'm assuming there is some sort of you go beyond X, and you'd have to rework the assumptions you're making.
So maybe we'll take it offline. I'm not sure exactly.
In the interest of time, let's take it offline. Yeah. Okay, let's thank the speaker again.